Next, we're going to show how to calculate empiric formulas. And don't panic. The calculation of an empiric formula is the backwards operation of what we just did, calculating the percent composition from the formula. In this case, you find the percentage composition and use the percentage composition to find the formula. First of all, what is an empiric formula? An empiric formula is the simplest formula for a compound. Now, you might remember a few weeks ago I told you there was the empiric formula, which is the simplest formula, and then there was the molecular formula, which is the actual formula. And we'll look at that in just a minute. So the steps for calculating or finding the empiric formula is as follows. First of all, you derive the number of moles of each element from its mass. So you are given a certain mass for each element that's in a compound, and you calculate the number of moles for each of those elements. So obviously it's important that you know how to do that, which is why we spent so much time talking about how to calculate the number of moles. Secondly, you divide each molar amount by the smallest molar amount to find the subscripts for the tentative empiric formula. Now what that means is let's say you do the calculation and you have 3 elements, and there's 1 mole of one element, 2 moles of another element, and 3 moles of a third element. The smallest of those 3 is 1, so you divide 1 into all 3 of those numbers, and that gives you the tentative empiric formula. The third step is you multiply those subscripts by an integer so that all the subscripts are whole numbers. You'll notice that we have not had any subscripts of any formula which were not whole numbers. So you need to end up with whole numbers when you do this calculation. So here's a diagram that basically shows the same thing. You have a compound that's made up of 2 types of atoms. One is A and the other is X. You start out by, on the left here, you divide each of those by the molar mass of each element, and it shows you end up with moles of A and moles of X. Then you divide by the lowest number of moles between those 2, and that gives you the molar ratio between those 2. And this molar ratio between the 2 represents the tentative empiric formula, and then you convert those to whole numbers by multiplying by a number that makes those numbers whole numbers. So let's take a look at something with numbers in it. Let's say that you're given that a compound consists of 13.5 grams of calcium, 10.8 grams of oxygen, and 0.675 grams of hydrogen. These are all listed on the left here as the given. So then you divide each of these molar amounts by their molecular weight or formula weight. Calcium, if you look up on the table, is 40.1, oxygen is 16, and hydrogen is 1.01. And you see that you end up with 3.337 moles of calcium, 0.675 moles of oxygen, and 0.668 moles of hydrogen. The smallest of those 3 is the 0.337, so you divide all 3 of those by the smallest one, and you end up with 1, 2, and approximately 2. And so the tentative empiric formula is CaO2H2, and those are all whole numbers, so you don't have to do anything else. So the tentative formula is CaO2H2, and as it turns out, that's calcium hydroxide. I just rearranged it. The bacterial fermentation of grain to produce ethanol forms a gas with a percentage composition of 27.29% calcium or carbon and 72.71% oxygen. What is the empiric formula for this gas? Now, this is taking the percentage composition and asking you for the empiric formula, and the percentage composition is actually written in a mass relationship. But let's see how we would do that. So first of all, you assume that you have 100 grams of the compound. That's because percentages are based on 100. So 27.29% is 27.29 grams of carbon in 100 grams. If you divide that by its molar mass of 12, you get 2.273 moles of carbon. And 72.71% is 72.71 grams of oxygen. And you divide that by 16 and you get 4.544. Then you divide by the smallest one, which is the 2.272, and you get 1 and 2. And so the empiric formula is CO2. Now, as I said before, the molecular formula is the precise formula, whereas the empiric formula is the simplest formula. The molecular formula is the exact formula and tells you the exact number of each atom in a compound. So to find the molecular formula from the empiric formula, after you've found the empiric formula and the formula mass for that empiric formula, you have to know the molecular mass, and you divide the molecular mass by the empirical mass, and that gives you a whole number, n. Then you multiply the empiric formula by that whole number n, and it gives you the molecular formula. So if you analyze a substance and it has the following composition, and I give you the grams of composition making up C, H, and O, you can find the empiric formula for that. Then if the molecular formula is 90, or the molecular weight is 90.079, what's the molecular formula? So let's look at how we would do that. Sorry about the quality of this writing here, but you can still see if you add up, you take each of these and you divide by the formula weight for each. So there's 6.9899 grams of carbon divided by 12 gives you 5.8196 moles of carbon. There's 1.1724 grams of hydrogen divided by 1.00794 grams of hydrogen in 1 mole, or 1.1631 moles of hydrogen. And then lastly, there's 9.309 grams of oxygen divided by 16 is 0.5818. The smallest of those three is, you can pick either one of these. Let's pick 0.5818. So you divide all of three of these by 0.5818 and you have 1 carbon, 2 hydrogen, and 1 oxygen. So the empiric formula is CH2O. And if you add up CH2O, the empiric mass is 30.026. If you divide that into the molecular mass that was given, you get the number 3. So you multiply the empiric formula by 3, and that gives you the molecular formula. Let's finish up with a brief discussion of solutions. A solution is a homogeneous mixture composed of a solute and a solvent. The concentration of a solution is the relative amount of solute in a given volume of solution. Molarity represents a measure of concentration, and it's defined as the number of moles of solute per liter of solution. Remember that definition, moles of solute per liter of solution. So vinegar is a solution of acetic acid, and that's the formula for acetic acid, in water. If you have half a liter of vinegar and it contains 25.2 grams of acetic acid, what is the molarity of this solution? Well, first of all, you have to find the moles of the solute. So the moles is 25.2. divided by 60.052. 60.052 is the formula mass for acetic acid. Then it's per liter, so you then have to divide by 0.5 liters because you only have half a liter, so you have this many moles in half a liter. You do the math and it's 0.839 molar solution, and molarity is represented by a capital M. Dilution is a process where you decrease the concentration of a solution by adding solvent. This formula that we're showing here shows you how to calculate a new molarity if you're given a certain initial volume and a final volume. So for example, the molarity of a solution times its volume is equal to the new molarity times the new volume. If you look at left versus right, the molarity of the graduated cylinder on the left times the volume of that solution is equal to the molarity of the new solution on the right times the volume on the right. You'll notice that the molarity decreases on the right and the volume increases. And you can, again, you can say it, the initial concentration times the initial volume is equal to the final concentration times the final volume. So if you have a 0.05 liter of 5 molar solution of copper nitrate, but you want to dilute that to a new concentration because you don't need it quite so concentrated, you would then add water to that. And you add enough water to that to end up with a new volume of 1.8 liters. So what is the new molarity? Well, the new molarity, again, it's the initial concentration times the initial volume is equal to the final concentration times the final volume. If you rearrange this so that you end up with the final concentration on one side and everything else on the other side, you'll have 0.85 times 5 molar divided by 1.8 liters for the new volume, or 2.36 molar solution. Let's finish with other units of concentration. There's something called a mass percentage. This is probably one of the simplest calculations. The mass percentage is the ratio of the component's mass to the solution's mass. So if you whatever the component you're talking about, if you're talking about, say, sodium hydroxide or whatever, it's the mass of sodium hydroxide divided by the mass of solution times 100. The volume percentage is the same idea, except it's the ratio of the volume of a component to the volume of the solution. Mixed mass volume units are commonly encountered in medical settings, and that's why we have to talk about it in this course, because in medical settings they frequently talk about mixed mass volume units. For example, sodium chloride is physiologic, that is the amount of sodium chloride in the body is 0.9%, and that's a mass percent. So it's 0.9 grams of sodium chloride in 100 grams of blood or water. The device shown on B here is a glucometer, which shows the concentration of glucose, which is measured in milligrams per deciliter. So you can see that there's all different mixed units that are used in medicine. You may have heard, particularly on television, something called parts per million or parts per billion. Parts per million is the ratio of the solute to solution mass multiplied by a million. It's the ratio of the solute to solution mass multiplied by a million. And parts per billion is the same thing, except it's multiplied by a billion.